This lesson is on differential motion equations, and it's basically doing differential equations but about motion, and specifically typically projectile motion, occasionally not, and we'll talk about that. But if we think about when we throw an object into the air, you know, what's happening. So we've dealt with motion, distance, velocity, and equation in here before. So things that you have to remember is that when it starts, its height above the ground is 0, or its distance is 0. And I probably, since we'll be using equations, should use function notation here. So our s of t equation will be equal to 0 here and here. And typically they'll ask us when it lands, and we'll use the fact that that distance equation is equal to 0 there to find when it lands. And also at the top, your velocity changes from being positive to being negative. And you know, you kind of see things hang in the air. It looks like a guy who's going up for a dunk may hang in the air at the top of his arc, and that's because for that split second that velocity is 0. And so a lot of times to find that highest point, we end up setting our velocity equation equal to 0 to help us out. Something I've mentioned in a previous lesson, but it may come up again. Acceleration due to gravity is negative 9.8 meters per second squared. Or if we're talking in feet, we'll be using negative 32 feet per second squared. So those are numbers that you need to know. Okay, let's move to an example. Okay, our first example is about dropping a stone from a 100-foot building. We want to know when it hits and how fast it's going at that time. So I'm going to write down what I know. If you are looking at when it is dropped, at the very instant that it's dropped, times 0, the distance above the ground is 100. So S of 0 is 100. Okay, also the instant that it's dropped, since it's dropped and not thrown, the velocity is 0. And that will increase as it gets closer to the ground. The velocity does, you know, change over time, but at that split second that it's let go, the velocity is 0, and then it starts to pick up speed. And then, since we are measuring this in feet, I'm going to use acceleration due to gravity. My acceleration equation is constant the whole time at negative 32 feet per second squared. And so this distance should be in feet. This velocity should be in feet per second. But again, this last one is, I'm putting a t instead of a 0 because at every second the acceleration is negative 32. It is constant acceleration. The velocity is going to change because of the acceleration, but the acceleration stays the same all the time. Now, let's look at the questions. First one is, when does it hit? Well, when it hits, as I was talking about before, we know that that distance is 0. And we normally would take our distance equation and set it equal to 0, but since we don't have a distance equation, we're going to have to work backwards to find that, and that's where the differential equations come in. So I'm going to start with my acceleration equation, and I'm going to take the antiderivative of both sides. So this will become velocity, and then the antiderivative of velocity here would be negative 32t plus c. And this is why we need this information that we wrote down. We know the velocity at time 0 is 0. So if I plug 0 in for the velocity and 0 in for the time, I realize that in this case c is 0. So my actual velocity equation is negative 32t and then plus 0, so just negative 32t. And so I'm going to star that. That's important. We have that now. But because we want to know again when it hits, and that's going to need our distance equation, I'm going to take this one step further and back up again and use my differential equation ideas. So Again, I know the velocity equation now. I can take the antiderivative of that, which gives me the distance equation. And then I just have to think about what that antiderivative is. So I'm going to use a power rule here, and that will give me negative 16t squared plus c. And I know now I can plug in at time 0, the distance is 100. So 100 equals negative 16 times 0 squared plus c. So c will equal 100. And then that means that my distance equation is actually negative 16t squared plus 100. So there's my distance equation. Okay, so now that I have those two equations, I can actually answer when does it hit. So for part A, when does it hit? We know it hits when the distance is 0, so 0 will equal our distance equation. And so I'm going to add that 16t squared to the other side, and then divide by 16, and then take the square root. Now, this is one of those cases, yes, you have the positive and negative square root, which square root of 100 is 10, square root of 16 is 4, so we're looking at positive and negative 10 fourths, but sometimes one doesn't make sense. So the negative 10 fourths does not make sense. And so we just go with 10 fourths. But since we're talking about time, it's probably better to get a decimal, which would be 2.5 seconds. So it hits at 2.5 seconds. Now, part B asks how fast it's going at that time. Since we know the time now, and we have that velocity equation, all I have to do is plug in. So the velocity at 2.5 seconds is just negative 32 times 2.5, which is negative 80, and I want to put units on that, and it's a velocity, so we're in feet per second in this problem. Okay, our second problem has an object that is thrown upward with a speed of 10 meters per second from a height of 2 meters. When will it hit the ground? So the first thing I notice is that we're in meters now instead of feet. But again, I'm going to start with writing down what I know. It's thrown upward, not dropped, so we have an initial velocity. So at time 0, it's going at a speed, a velocity of 10 meters per second. So the velocity at 0, 10 meters per second. It's also got a height. We're thrown from a height of 2 meters. So the height at 0 is 2 meters. And again, acceleration is something I know, and since we are measuring this problem in meters, I'm going to use the negative 9.8 meters per second squared for acceleration. Okay, again the question is when will it hit the ground, and so this is similar to what we did in the last problem with part A. And actually what we did before that, we have to get those equations. So let's start with our acceleration and take the antiderivative. So the antiderivative of acceleration will be velocity, and the antiderivative of the negative 9.8 will be negative 9.8 t plus c. And in this case, I had an initial velocity of 10, so when the time is 0, the velocity is 10. So I'm going to plug 10 in for the velocity and 0 in for the time, which means c is 10. So our velocity equation is actually negative 9.8 t plus 10. So I'll star that. And then I'll need my distance equation to find out when it hits the ground. So I'm going to start with the velocity equation that now we know for sure. And I'm going to back up and get my distance equation. So antiderivative of velocity is distance. And if I use a power rule here, I'm going to get negative 4.9 t squared plus 10t plus c. And I now have a height that I can plug in. At time 0, our height was 2, so I'm going to plug 2 in for the distance and 0 in for the time. And so in this case, I get c to equal 2, which means our distance equation is negative 4.9 t squared plus 10t plus 2. So there's our velocity equation and our distance equation. And the distance is the one we need because we want to know when this object will hit the ground. And so it will hit the ground when the distance is 0. So I set 0 equal to that distance equation. Now, this one's a little bit different because when you look at this, it's not as easy to solve as the previous problem, but it is a quadratic. So if it doesn't factor, which this one I don't believe does, you can, if you're in a non-calculator section, use the quadratic formula. I'm going to graph it and find the 0 that is positive because I believe it has also a negative one and we throw that out. So if you graph it and you calculate the 0, you should get time equals 2.224 seconds. When you're doing these problems, make sure that you are putting units on your answers and getting in that habit. Not every single problem is going to be exactly like these two. You have to use your common sense knowledge of motion to be able to plug things in. But the differential equation steps are pretty much the same as what we've been doing in our previous lessons. But just give each one a shot and make sure to put your units in. That concludes this lesson.